All right, well, now we're starting with Chapter 2, Section 4, and the first thing that we want to look at is something that we call the atomic mass scale. And this is a way for measuring the really small objects of atoms. So the atomic mass scale. We're going to start with something that we call the atomic mass unit, or the AMU. And the definition, and you'll notice there's a little asterisk here, so pay attention to that. I'll talk about that in a second. But the definition is exactly 1/12 the mass of a single atom of carbon-12. That is the atomic mass unit. So 1/12 the mass of a carbon-12 atom. Now, a carbon-12 atom has 6 protons, 6 neutrons, and 6 electrons. And if you put those all into an atom and measure its mass, it comes out to exactly 12 AMU. Now, officially, the unit is called the Unified Atomic Mass Unit, and we use the symbol U. But this text uses the older abbreviation AMU, but we're going to just make those interchangeable for purposes of this class. All right, well, 1 AMU is approximately 1.66053,907 times 10 to the negative 24 grams. It's very, very small. And 1 gram, and this one really is approximate, and I'll explain why that is later, but 6.022140076 times 10 to the 23rd AMU. And it's just a reciprocal of the number that's up on top. If you put this number in the calculator and take 1 over it, you will get this number. And that is Avogadro's number, a number that we will talk about in great detail in the next chapter, in chapter 3. Okay. All right. So now what we want to do is we want to look at how do we measure the mass of these little tiny objects, these atoms, because we can't just take a single atom and put it on a balance and measure it. If you look at the balance that you have in the lab or the one that you have in your kit, if you're taking this online, you will find that there's no way you can measure, you can't set the units to atomic mass units because that's way too small. The way that we do it is to use something that is called a mass spectrometer. A mass spectrometer. The way that a mass spectrometer works is that we simply put, we get a vacuum chamber here. So there's a vacuum pump. We pump all the stuff out of here. And then we use a needle to inject a small amount of the element in this case. You can do this with molecules. We'll save that for another point in your life. But you do this with the atoms. There's a beam that will ionize it, break it apart so to make sure that it is atomic form and not molecular. And what that electron beam does is it removes an electron from the atom and makes it have a positive charge. Now, normally chlorine doesn't have a positive 1 charge, but in this case, it can do that because this is a very unusual situation. Sometimes this thing will remove 2 electrons. And when it removes 2 electrons, you'll have a positive 2 charge on there. And when that happens, it just doesn't show up on the graph. So we don't need to really worry about it. Well, those positively charged particles can be accelerated using a strong magnetic or a strong electric field here. It can be accelerated to a very high speed and then goes through a slit and through another slit. So we have a very fine beam of particles that contain both chlorine-37 and chlorine-35. And since they are charged particles that are moving through space, if they go through a magnetic field, that magnetic field will cause those charged particles to change direction. There'll be a force that is applied on those particles and they will change direction. When those, the amount that they change will depend on 1, how fast it's going, and 2, on the strength of that magnetic field. By varying the strength of the magnetic field, you can sweep through a couple of different values and measure all of your isotopes. All right, so here they sweep through. You'll see that the chlorine-37 that's heavier doesn't bend as much. The chlorine-35, which is lighter, it bends more, and it hits this slit. And when it goes through the slit, it hits a detector, and then you can tell that particular isotope was present. You can even tell how much is present by looking at the intensity of the signal on that detector. Now, in case you're wondering, like, that doesn't make any sense, don't worry. I'm going to explain it in a different way here in just a moment. And by the way, how do you measure the chlorine-37? Well, by changing the strength of that magnetic field, you can get, like I said, you can sweep through a range of values and get and measure the different values on your mass spectrometer. All right, here are the masses as accurately known as possible given the current limits of instrumentation. Here are the masses of chlorine-35 and chlorine-37, the two isotopes of chlorine that exist on Earth. So chlorine-35 and chlorine-37. It turns out the rest of the isotopes of chlorine are radioactive, so we don't get chlorine-36, in case you're wondering. All right, so these are the masses and this many atomic mass units. And you'll see there are a ridiculous number of significant figures here, and that's normal. That is perfectly normal for a very high-end piece of equipment. Now, if you have a mass spectrometer and let's say you only want to get to the nearest whole number, which usually that's enough information for a lot of things that you might do. If you just want to get to the nearest whole number, you can get yourself a mass spectrometer for under $20,000 in case you're looking to get one for your house. It's, kind of expensive. All right. If, on the other hand, you want to get one that goes out to the 10,000s place, so where this 8 and that 9 are right there, if you want to go out to the 10,000s place, you would need to spend on the order of, let me see here, it was about $2.5 million, but that was about 13 years ago. So it probably over 3 million, $3.5 million to go out there. To go out to this many digits, you're going to need a big room and tens of millions of dollars, and it's probably going to be a specialty made object. So going out to that many digits, not many of those exist. If you need to have that measurement made, you would work with somebody. But those are one of a kind pieces of equipment. Each one is unique. All right. So getting all those numbers, that is something that that different scientists have set up their instruments to do. Now, the abundance of these is usually given in percentages, and the percentages are going to be determined by the intensity of the signal that hits the detector. And so by getting the relative intensities of those signals, you can get these relative abundances. These abundances are the abundances, the averages on Earth, and the uncertainty is in the hundredths place here in these percentages. And so we only have 4 significant figures in each of these numbers. So there is uncertainty in that 8. And I will show that to you on this page. So I'm going to go over to chlorine here. All right. This is Web Elements, and this is the chlorine page on Web Elements. If you haven't checked out Web Elements, just go to webelements.com and you can click. There's the whole periodic table, and you can click on any particular element. I'm going to go back and click on chlorine, and it has some background information on chlorine. It has all the other elements if you want to go click by name, and then it's got all this background information, and then it's got these sub pages that you can go to and look at the physical properties, thermochemical properties. I'm going to go down to let's see, that's abundance in nature. I want to find isotope data. Right here, isotope. So chlorine isotope data. So I'm going to click on the more isotope data. And if you come down here and look, you'll see the numbers that I just showed you. So that the numbers I just showed you on that other page are listed here. And then these are the abundances. The numbers in parentheses are the uncertainty in those numbers. So like this means plus or minus 4 in that last digit. This means plus or minus 69 in these last 2 digits. So anyway, that is where I got that information. Has other information too. It even shows you what are the known isotopes and which are radioactive. So all these other ones are radioactive. You'll see that there is a certain amount of so chlorine-40 is radioactive. It has a half-life of 1.38 minutes, so it doesn't stick around very long. So the only ones that are really measurable in any significant amount on Earth are these. By the way, if you were to go to a different planet or even to the moon, you might find these numbers to be slightly different. You might have slightly different isotopic abundances depending on where those elements were formed. Now, if you go to our moon or Mars or something, since all of our planets were likely formed from the condensation of the same star or debris from a star, then we probably have the same isotopic abundances. But if you were to go to a different star system and a different planet, you might find that these numbers would be slightly different. Kind of interesting. In any case, that's where I get those numbers. So I'm going to go back over to here, and we want to see how it is that we use these numbers. We want to get the average atomic mass. So the average atomic mass. I'm going to pull up my periodic table here. So here's our periodic table. And if we look, chlorine has an average atomic mass of 35.45. The way that we get that 35.45 is to use these isotopic masses that I just showed you, and to use these abundances, the isotopic abundances. And by using those, you can get the average atomic mass. If you just take these two numbers, add them together, and divide by 2, you will get a number that is not the correct number. So you don't want to do that. So calculating the average atomic mass, you simply do what's called a weighted average. So you multiply the fractional isotopic abundances by the average, the mass of each isotope, and then add them together, and you will get a weighted average. So here are the masses that were given on that other page. And then here are the isotopic abundances. And then to do the fractional, we're going to need to take these percentages and make them a fractional number. In other words, we'll take the percentages and divide by 100. So this will become 0.7578. And this will be 0.2422. So you'll take this mass, multiply by this fraction, so by 0.7578, and then this times the 0.2422. Since this has a whole bunch of sig figs, this only has 4. That means the number that you get here is only going to have 4 sig figs. This will only have 4 sig figs. And then we will add those numbers together. And when we add those numbers together, this one goes to the hundredths place, that one goes to the thousandths place. So we would round it to the hundredths place. And so that 35.45, that is how we get this 35.45. All right. In case you're wondering, that is how we get that 35.45. All right. And as I mentioned, there is a little bit of uncertainty in that 35.45. So, 35.46, 35.44, it's going to be close to that number. There's uncertainty in that last digit. That's fine. That's fine. All right, so now let's look at number 33 on the in-class assignment. Here we want to do the average atomic mass of magnesium. So we want to calculate the average atomic mass. So we're going to take each of these. We've got magnesium 24, 25, and 26. Here are the atomic masses, and then here are the abundances. And then we're going to do, let's see, 23.98504 times 0.7899, and then 24.98584 times 0.1000, and then 25.98259 times 0.1101. And that takes up the 3 known isotopes. Now, if you just take these numbers and punch them into your calculator, so 23.98504 times 0.7899 plus 24.98584 times 0.1000 plus 25.98259 times 0.1101, we will get a number, and that number is 24.30505, and I'm not going to write all the numbers. All right, but that is not rounded to the correct number of significant figures. To round this to the correct number of significant figures, I'm going to do a subtotal over here so we can pay attention to how many sig figs we're supposed to have. So I'm going to clear that information, and it will do 23.98504 times 0.7899. And then I'm going to hit enter. And since we have since we have a bunch of sig figs and 4 sig figs, this should have 4 sig figs. So we'll call that 18.95. So 18.95. All right, next we'll do 24.98584 times 0.1000. And not surprisingly, that's going to give us 2.49, and we'll round that to 9 there. Next, we'll have 25.9825, so 25.98259 times 0.1101, and that gives us 2.861. All right. And we're going to add those numbers together. So 18.95 plus 2.499 plus 2.861. Now, we should get a number that's pretty close to what we got here. Yeah, so 24.310 is the number there. Now, when we look here, this goes to the hundredths place, thousandths place, thousandths place, so we should round that to the hundredths place, so we'll call it 24.31. All right, this is the answer with the correct number of significant figures. So that's the answer with the correct number of significant figures. If you go to your periodic table, and here is magnesium at 24.305, this is the commonly accepted value, so I just put that in there. So 24.305. Really, we have a little bit of uncertainty in that hundredths place, which is why it's probably best to write that to 0.31. You'll see you get more of those digits here when you do that. But as far as the correct number of sig figs, 24.31 is probably the best we can do with our rules for sig figs. So that is how we do that calculation. If you're doing a problem like this on your homework, you know, make sure you work it out and write everything out. If you're doing a problem like this on the test, because you're going to have a problem on the test, here is a word of warning. 1, don't just take the numbers, add them together, and divide by the total number of numbers. That is guaranteed to give you a wrong answer. And since our tests are multiple choice, it will give you one of the wrong answers on the exam. So you don't want to do that. The other thing I will caution you about is that the element that you're going to get on an exam is not going to be a regular element. It's going to be a fictional element. And so you can't go and just check on the periodic table to get your answer. So like, I'm not going to give you magnesium or chlorine. You're going to get one that is a fictional number, and you'll have to make sure you do the calculation correctly. So know how to do weighted averages with your isotopic abundances and isotopic masses to give you the your average atomic mass. All right. So now that we've done that, all right, we want to look at the periodic table. So the periodic table, there's a couple of features on the periodic table that you want to be familiar with. All right, first of all, the horizontal rows across the periodic table are called periods, and the vertical columns on the periodic tables are called groups. So those are group numbers up on top, and the period numbers are down on the bottom. Now, about those group numbers that are up on top, there's two predominantly used grouping number systems. There is sort of the old system that is used primarily here in the United States, but in some other countries as well, where this is group 1A, 2A, and then we come over here to boron, 3A, 4A, 5A, 6A, 7A, 8A. And then the transition metals are going to have the headings of B. So 3B, 4B, 5B, 6B, 7B, 8B, 1B, 2B. Now, interestingly, there were a fair number of people who were in Europe, and they used a different system where it was 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. And this was 1B, 2B, 3B, 4B, 5B. Since we had two different systems, there was a group that's called the International Union of Pure and Applied Chemists. They came up with a new way of doing this, and they just decided to renumber it, and this is going to be group 1 through 18 for each of those vertical columns, and then that's it. That's it, and that's how you number it. Unfortunately, most of us, I don't know if it's unfortunate, but most of us who are chemists kind of like the old numbering system. And there's reasons for that. For example, carbon has 4 valence electrons. If you're not sure what valence electrons are, don't worry. You'll know what that is later. But it has 4 valence electrons, and it's in group 4. And if you use the 14, you kind of lose that information. So, all right. So I typically will use the group numbers that include the letters. And if I say group 4, I'm talking about carbon. If I want to talk about the group with titanium, I will either call it the titanium group or group 4B specifically. All right. In addition to this, we also have other information that is color-coded into the periodic table. And so if you look at all of these elements here that are kind of a beige color, those are all metals. The ones that are along the stair step here, those that are in light purple, those are metalloids. And the ones over here that are in the light green color, those are non-metals. Now, for the periodic table that I have prepared for the class, so here is a printed out version of that periodic table, which you can download and print out yourself. I use that same color coding system, or at least similar color coding system, but I also add one more useful bit of information. And that one more useful bit of information is the element, the name, the color of the symbol tells us what state it's in. So solids have black letters. The 2 blue ones, bromine and mercury, those are liquids, and these red ones are gases. Now, unfortunately, with the color that I picked out for these other ones, so like francium, lawrencium, rutherfordium, all right, all of those are unknown. You just can't get enough of those samples to determine if they are solid, liquid, or gas. Sometimes some books will just estimate, but if it is unknown, I do not put what it is, because that you just can't measure. You can't measure the melting point of francium. You can't measure the melting point of moscovium here. All right. Moscovium is one of the least characterized elements in existence. So, all right. So there you go. That is some useful information. The average atomic masses are given on here on this periodic table, where on the one that was on the overhead a minute ago, it was not given up. And then, of course, the atomic numbers are given as well. When it comes to reading the periodic table, so each box will have the atomic number and the symbol. And just as a reminder, the atomic number and the symbol are, it's a 1-to-1 matching. All elements with exactly 19 protons are potassium, and all potassium atoms have exactly 19 protons. So, and then the atomic weight, again, that is terrestrial. So that will be average atomic weight on Earth. And as I mentioned, it may be slightly different at different locations. The whole reason that we call it a periodic table is because the properties repeat periodically. Now, I won't say it repeats. It's kind of like history. History doesn't repeat, it rhymes. Well, the periodic table, it doesn't really repeat, it rhymes. It has similar chemical and physical properties. So we'll find that elements that are in the same group have similar chemical and physical properties. That's not always true, but it's usually true. Just as an example, as you're going through the periodic table here, if we go to here, we've got a non-reactive gas, and then the very next element is a soft reactive metal. Well, helium is a noble gas, and lithium is an alkali metal. If we go a little further, we'll find a non-reactive gas, another noble gas, and a soft reactive metal, sodium. And then we'll do it again, argon and potassium. And if you go a little further, you will get to, let's see, krypton and rubidium. You'll have that same repeating pattern. Now, again, the properties aren't identical, but they have similar properties. So they have similar properties. In addition to these names, we in addition to the group numbers, we have a naming system. And that naming system gives family names for each of the groups. So group 1A is called the alkali metals. Group 2A is called the alkaline earth metals. Group 6A is called the chalcogens. Group 7A is called the halogens. And group 8A is called the noble gases. And so sometimes you will see these names. And I want you to know these names. So I want you to know these names. So if I say, what family is helium in, and you would say, oh, helium, it's in group 8, and helium is a noble gas. All right, so I want you to be able to do that. So make sure you know those 5 names, those groups by their names. All right, so the next thing that we want to look at is molecules, and we want to differentiate between molecules and non-molecular substances. So when it comes to molecules, these have covalent bonds. So they're elements that are connected by covalent bonds. And here are some examples of some molecules. We've got a couple of elements up here. Hydrogen and oxygen are diatomic elements. So they're all. If you find elemental hydrogen and elemental oxygen in their ground state, you will find that they are diatomic. Here are some molecules: water, hydrogen peroxide. So these are what the molecules look like, and we can indicate how many of each atom are in there by writing the molecular formula. All right, we're going to talk more about this in chapter 8. Most of the time, if you've got a molecule, it contains either only nonmetals or nonmetals and metalloids. Okay. So mostly nonmetals or nonmetals and metalloids. I'm going to switch back over here. So mostly the green things, but sometimes some of the purple things as well. However, I am going to say this, it's complicated. There are molecular compounds that have metals in them. And for example, the bond between gold and sulfur is typically a covalent bond, and in fact, it's not even very polar. So, so we will find some significant covalent bond character, particularly among some of these elements that are here in the middle. However, if you have a bond between like a group 1 or group 2 metal and something that's a nonmetal, it almost certainly is going to be an ionic bond. And so we want to treat those ionic bonds a little bit differently. So relationship status, it's complicated. All right. I want you to know the 7 diatomic molecules, 7 diatomic elements. There are 7 elements when they're in their elemental form and their lowest energy state. They are going to be diatomic, meaning that there will be 2 of the atoms. And these are hydrogen. Hydrogen's kind of off by itself, but then the others are all grouped together here. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. We will find that all of those are going to be diatomic. Now, most of the other elements are monatomic, but there are a couple of them that are different. Like phosphorus, for example, is tetraatomic. It's P4. And sulfur, that's kind of interesting. So here, phosphorus is P4. Arsenic is As4. Let's see. Sulfur usually has 8 atoms in its molecular form. So it's S8. There you go. So I point that out. There's some other ones. You don't have to know those. You have to know the diatomics. So you have to know your diatomics. So know these. Memorize these. All right. You will be expected to know these as we move forward. Now, we want to look at something that we call the empirical formula and contrast that with the molecular formula. The empirical formula simply gives you the lowest whole number ratio of the atoms in a compound. It can be an ionic compound, it can be a molecular compound, but the empirical formula is the lowest whole number ratio. For example, with the molecule H2O, O2. So hydrogen peroxide, H2O2. Since they both have a subscript of 2, that's not the lowest whole number ratio. We would need to take that number and divide each of them by 2. And so our empirical formula for hydrogen peroxide would simply be HO. All right, so that's our empirical formula. Again, lowest whole number ratio. Molecular formula, on the other hand, if you have a molecular compound, it tells you the exact number of atoms in each element of that compound. And so the molecular formula is a bit different. And so for molecular formula hydrogen peroxide, it would simply be H2O2. All right. So let's go to number 41 on the in-class assignment. And here on number 41, we want to look at this and determine, is this the lowest whole number ratio? All right. First, we want to make sure that all the elements are together. So Al2Br6, that's fine. And then when we look, the coefficients are 2 and 6. And since those are both divisible by 2, that means that we can divide them both by 2, and we could simply write AlBr3. And so that would be the empirical formula for aluminum bromide. On this one, C6H12, well, so you see that they're both divisible by 6, so we could divide them both by 6, and we will simply get CH2. So CH2. Now, one of the downsides of using the empirical formula for molecular compounds is that you lose a little bit of information. C6H12, I mean, there's a whole bunch of different compounds that have that formula, but we could narrow it down. But CH2, there's a lot more compounds that have that empirical formula, and so you lose a little bit of information. All right, let's look at the next one. On the next one, we're going to need to do some combining, but because you see here we've got carbon and carbon, we have hydrogen in 2 places, and then 2 oxygens. So we're going to combine those, and we'll do C2H, and we have 3 plus 1, so 4O2. And now when we look at that, C2H4O2, those are all divisible by 2, so we could write CH2O. And it turns out that there are a whole bunch of compounds that have the empirical formula CH2O. This one is acetic acid, so CH3COOH, that is acetic acid. It gives us a little bit of extra information by having that, but empirical formula is CH2O. Let's look at this one. Our subscripts are 4, 8, and 1. Remember, when there's not a number written, it is implied to be 1. So, since there's not a number written there, our coefficients are 4, 8, and 1. Since one of those is 1, that means our empirical formula is the same as our molecular formula. And that does happen on occasion. So C4H8O is the empirical formula as well as the molecular formula. C6H12O3, well, those are all divisible by 3. So if we divide them by 3, we'll have C2H4O. So C2H4O. And then finally, B3N3H6, those are all divisible by 3 as well. So it would be BNH2. And that is our empirical formula for B3N3H6. When we go beyond molecular formulas, so if we want to look beyond molecular formulas, we have something that is called a structural formula. It tells us the connectivity of the atoms. So it tells us what atoms are connected to what other atoms. So for example, the molecule CH4, we have 4 hydrogens that are directly connected to a carbon atom. We also have what are called perspective drawings and ball and stick models. The structural formula does not tell you the shape of the molecule. But if you have a little bit of extra information, you can determine what that shape is. And with that, you could get a ball and stick model, and you could do a perspective drawing to tell you what that shape looks like. So this ball and stick model, as you can tell, this hydrogen is coming out towards you. The one in the back here is going back away from you. And I've actually got one of these. Bear with me for a second. I've actually got one of these. Let's see if this works here. All right, so I've got a CH4 molecular model here that we use a little bit later in the semester. and it shows the connectivity. So we've got 4 hydrogens, which are the white atoms. The black atom is a carbon atom, and they're all attached. But it shows you what the shape is. Interestingly, we'll find that the shape between this bond, or the angle between those two bonds, is not 90 degrees. It comes out to about 109.5 degrees. So 109.5 degrees. And you'll see one that's coming towards you, and then one that's back here in the back going away from you. So this is represented by this ball and stick model. However, if we had to represent every single molecule by drawing the ball and stick model, that would be a little bit challenging. So once we get used to that, we can do something that we call perspective drawing, and that is a simple way of representing the shape in a 2-dimensional drawing. Very simple way to do that. All right. And then finally, it turns out that that ball and stick is not really what the molecule looks like, because the electrons take up a lot more space. We don't have sticks between the atoms. And so we can use something that's called space filling models, and that gives you a more accurate representation of how those atoms take up space. We're going to talk about this in a lot more detail in chapters 8 and 9. Chapter 9, we'll get to the shapes. So that's coming up later this semester. All right, ions and ionic compounds. So now what we want to do is we want to look at what happens when atoms lose or gain electrons. For example, the atom sodium, it tends to lose an electron, and when it loses an electron, it becomes a positively charged particle, and we call positively charged particles cations. And please note that that cation has a hard T sound, so it is cation. Sometimes people look at that and they think, what's a cation? No, it is a cation, a positively charged particle. For the negatively charged particles, so like, for example, chlorine has a tendency to pick up electrons, and when it does, it becomes the chloride ion. And negatively charged particles, those negatively charged particles, we call those anions. And we don't want to call them anions. We want to call them anions. So those are anions. All right. If you know the number of protons and electrons in an atom, if you simply take protons minus the number of electrons, so number of protons minus the number of electrons, that will give you the charge on the species. So for example, up here, 11 minus 10 is positive 1. So there's a positive 1 charge on the sodium. Here on chlorine, 17 minus 18, that's negative 1, and we have a negative 1 charge on chloride. So we're going to look at number 47. All right, so here is number 47. And this is going to be very similar to what we had done. On the previous page. But on this, the number of electrons and the number of protons are not going to be identical. So we'll start here with cobalt 59. And it has a positive 3 charge. You'll notice that when we have a positive 3 charge, we always put the number before the symbol for the charge. So we put 3 plus instead of positive 3. So down here for the net charge, I'm going to put 3 plus. All right. Cobalt is right here. It's element number 27. That means that there are 27 protons in cobalt. So 27. 59 indicates, let's scoot this down a little bit. There we go. I had scooted it out when we were looking at those models. Forgot to scoot it back down. So 59 is the mass number. That's the total number of protons and neutrons. So 59 minus 27 gives us 32. And then the number of electrons, since it's a positive charge, the protons is going to be bigger. So 27 minus 24 gives us positive 3. So there's got to be 24 electrons. So 24 electrons. All right. So let's do the next one. So 34 protons, 36 electrons. So 34 minus 36 gives us 2 minus. Element 34. Get our periodic table here. Element 34 is selenium. So we're going to put Se, 2 minus. And then to get the mass number, we'll simply add the number of protons and neutrons. So 34 plus 46 is 80 And so that is selenide 80. So selenium, 2 minus charge, and mass number is 80. All right, for our next one, let's see. We have a 2 plus, so we have fewer electrons than we do protons. So 76 minus some number will give us positive 2. That's going to be 74 electrons. And then element 76, we'll come back over here. Element 76 is right there. It is osmium. So I'm going to put OS. And we already know that that is a plus 2 charge. So osmium 2 plus. And then our number of protons plus our number of electrons, that's going to come out to 192. And I should double check that just because, you know, math and stuff. Let's see, 76 plus 116, 192. All right. Next, element number 80. Let's go ahead and get the charge here. 80 minus 78 gives us 2 plus. So that is 2 plus. And then here, element 80. Come back over here. Element 80 is mercury. So that's going to be mercury 2 plus. So Hg 2 plus. And then to get the isotope, we're going to add the number of protons and neutrons there. I don't need a calculator for that. That's simply going to be 200. So 200. All right, next. Here we've got all the information. We've got phosphide, which is P3 minus, and there's 31 is our mass number. Phosphorus is element number 15. All right, so there's 15 protons. And the number of neutrons is going to be 31 minus 15, so that's 16 neutrons. The net charge is 3 minus, and in order to get 3 minus, it'll be 15 minus 18. So we'll have 18 electrons there. So 15 minus 18 will give us negative 3. All right, our final one here. We've got a positive 3 charge. There's 76 electrons. That means there must be 79 protons. And if we come back over here and we look, element 79, that is gold. All right, so gold is Au 3 plus. And then we'll add these two numbers together. So 118 plus 79 gives us 197. I had a little mathematical fail there for a second, but yes, 197. So gold 197, and it has a 3 plus charge. All right. We'll do one more little section here before we end this video. All right, so there are certain elements on the periodic table that always have the same charge. And for these, I want you to memorize these because they always have the same charge if they are monatomic ions. And so, for example, in group 1, lithium, sodium, potassium, rubidium, cesium, they're always going to be +1. You'll never find sodium +2 in any compound. In a similar fashion, these group 2, magnesium, calcium, strontium, barium, they're always +2. Interestingly, beryllium, which is also in group 2, it tends not to form ions very well. So it tends to form molecular compounds just because of its nature. If we come over here, let's see, aluminum is going to be +3. And then if you have nitrogen and it's a monatomic ion, it's going to be nitride, and it's going to have a -3. We'll talk about naming here in the next section. So nitride, -3. You can form a 3- on phosphorus, which is right below it, to be P3-. So that is a possibility. Group 6, it's usually 2-. So oxide is 2-. Sulfide, selenide, telluride, those are all 2-. Group 7s are usually -1. Hydrogen can either be +1 or -1, so you just have to look for the context clues when you're working on it. And then there's a couple of the transition elements, transition metals that end up having the same charge. Scandium is always +3. You'll never find scandium 4. You'll never find scandium 2. It just doesn't really work. So scandium 3 is almost always where you're going to run into. For zinc and cadmium, they're always going to be +2. And then for silver, it's always going to be +1. All of these other ones that are blank, those can have more than one charge, or at least most of them can. So they can have more than one charge, and we'll just have to treat them a little bit differently. If you know these, if you memorize these, you're going to be a much happier person when you're working on problems. So memorize these, and it's not too hard to memorize because they're grouped together. All right, so like I said, all the other ones can form more than one charge, and I want you to know these. So when it comes to ionic compounds must be electrically neutral. They have to have the same total positive charge and negative charge. You can't have excess positive charge or excess negative charge. So for example, if you form a compound between magnesium and nitride, well, magnesium has a 2+ charge and nitride has a 3- charge. Well, if you take one of the magnesiums and one of the nitrides and stick them together, you're not going to have a neutral compound. You're not going to have the same amount of positive and negative charge. You'll have excess negative charge. Well, that doesn't work. So what happens is that we have to come out where we have to make it so that these have the same amount of positive charge for the magnesium as we do for the nitrides. And the way that we can do that is we can do a little trick that's where we take whatever the superscript is on one and make it the subscript on the other. So we can take the superscript on magnesium and make it the subscript on nitrogen. And likewise, take the superscript on nitrogen and make it the subscript on magnesium. And when you do that, you will get Mg3N2. This is kind of like cross multiplying, right? When you get a algebra problem and you want to solve for, you get two ratios that are equal to each other. You want to solve for something. Well, you can cross multiply. Well, this is kind of like cross multiplying. So 3 times +2 is +6. And 2 times -3 is -6. And so that adds together to give you 0. Now, sometimes if you're trying to get the empirical formula, sometimes when you when you cross these things over, you may get it so that this is not the lowest whole number ratio. And if it's not the lowest whole number ratio, that means that you are going to need, if it's not the lowest whole number ratio, you are going to need to divide by the greatest common factor. Okay. Now, the other approach you can take to this is if you look at the numbers here, the superscripts, the charges, if you say, all right, 2 and 3, what is the least common multiple of 2 and 3? Well, the multiples of 2 are 2, 4, 6, 8, so on and so forth. And the multiples of 3 are 3, 6, 9, 12, 15, and so on. Well, the smallest number that's on both of those lists is called the least common multiple. This is something you've learned in math, but you may have forgotten it. So that least common multiple, whatever that least common multiple is, if you multiply these by by a number to give you the least common multiple, then you will get the empirical formula. So if the least common multiple is 6, so whatever times 2 gives you 6, that's 3. Whatever times 3 gives you 6, that is 2. And you'll get the same formula. Let's do number 57. All right, so here is number 57 on the in-class assignment. When you're writing out the empirical formula for these compounds, you always want to put the cation first and the anion second. We just do that by convention. We never put the anion first. We always put the cation first. So we're going to put the cation first and then the anion second. So potassium's +1, chloride is -1, it's +1 -1. It's just going to be KCl. So that one is KCl. So +1 and -2, well, that means we're going to have K2O. K2O. +1 and -3, we'll have K3N. So K3N. I have never in my life seen potassium nitride, but I suppose in theory you could get it. I don't know if you could purchase it though, but I've never seen it like in person. All right, next one. Ca is 2 plus, chloride is minus 1. So we're going to need 2 of those chlorides, so it'll be CaCl2. Calcium's plus 2, oxide is minus 2. Well, the least common multiple of 2 and 2 is 2, so we just need 1 of each. It'll be CaO. And then here we've got Ca 2 plus, and nitride is 3 minus. And so we'll have Ca, so the least common multiple of 2 and 3 is 6. So we'll have Ca 3 and 2. So Ca3 and 2. All right, and then here we've got Al3 and then Cl. So we're going to have, 3, and we need 3 of those chlorides, so we'll have AlCl3. Al is 3 plus, oxide is 2 minus. The least common multiple of 3 and 2 is 6, so we'll have Al2O3, aluminum oxide. And then Al is 3 plus, nitride is 3 minus. The least common multiple of 3 and 3 is 3, so we just need 1 of each. It'd be AlN. All right, now for lead. So Pb4 plus, chloride is minus 1. It would be PbCl4. Pb4 plus, and then oxide is 2 minus. So the least common multiple of 4 and 2 is 4, so we'll need 1 of the leads, so Pb, and then 2 of the oxygens, O2. So PbO2, and that's lead oxide. And then Pb is 4 plus, and nitride is 3 minus. The least common multiple of 4 and 3 is 12, so we will have Pb3 and 4. So Pb3 and 4. And that would be our lead 4 nitride. All right. So I'm going to break the video off at this point, and then we will do the next section about nomenclature. Pretty sure that's nomenclature. Yes, we're going to do the next section about nomenclature on the next video.